always get nervous when people clap when you get up and you haven't said anything. The normal reaction to this is I should sit down because it won't get any better than that. Let me first start out by thanking you for an opportunity to talk this afternoon. I hope that you aren't expecting an extremely deep, comprehensive discussion about architecture. If you are, you can go to sleep now, because I certainly don't anticipate trying to do that in the time I have available. What I do want to do, though, is to try to underline maybe some principles, some notions, some ideas, some issues that I hope all of you will keep in mind as you struggle to figure out how we should design and build such a complex system. It is a massive transformation in many respects of what we have lived with for the last, roughly speaking, 100 years. So you are undertaking a remarkable enterprise which could have extremely long-lasting impact on the way in which not only American society, but perhaps societies around the world experience their use, not only of electrical power, but other resources as well. I wanted to begin by calling this Only Connect, and to draw attention to a literary phenomenon, a man named E.M. Forster. If you don't recognize the reference, let me encourage you to Google Only Connect and Forster and learn what this was all about, a philosophical point of view that many solutions to our problems require us to connect with each other. And certainly in the process of developing standards, it is the connection between us and our shared understanding of the problem space and our willingness to give credibility to each other, to trust each other's motivations, to want to get to consensus. Everyone may be motivated by different things. Some of them will be pecuniary motivations, some of it will be corporate, some of it may be personal. But in the course of trying to establish standards, one of the things that's very important, I think, is that we start out from the premise that people's intentions are good and credible. Now, I know that sounds a little Pollyanna, but it's very, very hard to do standards without at least starting out on the presumption that the other guy wants as much as you do to come to some kind of consensus. Of course, we all understand that sometimes that's of the form, I want to come to consensus as long as you agree on what I want to do. That's, of course, the place where leadership is needed in the various working groups and TAPs and the like. So please do look up E.M. Forster. By the way, he also wrote another book, which I draw to your attention, called The Machine Stops. And this was about a society in which everyone was housed at home and fed remotely at home. They never went anywhere out of their homes because they interacted with each other through this machine. Now, this was written around the turn of the previous century, so in the 1900s or so. And The Machine Stops is all about what happens to that society when this machine doesn't work anymore. And we don't want that to happen with the smart grid. We don't want the grid to stop. We don't want the systems that we are relying on to stop. So you should read a little bit about what the side effect of that was sociologically. Let me start out by taking you back into history for just a moment. This is the first 4 nodes of the ARPANET project. What many people may not appreciate is that it was motivated by resource sharing. The Defense Department was sponsoring many computer science departments around the United States to do research in artificial intelligence and computer systems design, programming languages and the like. And every one of the institutions insisted that they had to have a world-class machine in order to do world-class research. And so they would say every year they expected to get a new computer. Now, back in those days, in the late 60s and early 70s, machines were millions of dollars. They occupied 1 or 2 or 3 rooms, needed special cooling and everything else. So even ARPA, with its budget, could not afford to buy a brand new machine for every one of these dozen or so departments. So they said, why don't we find a way so they can share? And to do that, they decided to go down the path of building a packet switch net, which was not at the time the conventional wisdom. The conventional wisdom at the time was you built networks using circuit switching technology, just like the phone network, but that didn't look like it would be responsive to the kind of dynamics of computer networking or computer communications. So this was the first 4 nodes, and it really was motivated not by building a network to survive a nuclear attack or anything. It was to share computer resources among a collection of people. Of course, as we got further into that exploration and packet switching worked well, the internet was designed and built and propagated. And here you see an automatically generated view of the connectivity of the internet, different colors for different autonomous systems. And the point here that I want to emphasize is that this is not a centrally controlled system. It's very distributed, it's very collaborative. People voluntarily connect to each other on this network. The reason they do that is that it is, from their point of view, for a variety of reasons, beneficial to be part of that system. So it is highly collaborative and highly dependent on people's willingness and agreement to interconnect in this way. And I would suggest to you that a successful smart grid effort will have that characteristic as well. That it's important that there be reasons why appliance makers, power generation and distribution agencies want to interconnect and engage in the use of this new technology that you're working on. So collaboration is going to have to be an important element. This is not going to be something we can force on anyone, no matter how hard we try. This is relevant to another point I want to make in a moment. This is the rate at which computers have been added to the internet. It's slightly misleading in the following sense. These are the machines that you can actually see on the public internet. There are probably many more that are hidden that you can't see in the public net because they're behind firewalls, or in Google's case, we have a lot of machines in our data centers that don't actually appear on the network with IP addresses and public domain names. So the actual number of machines on the net is larger than this, but the doubling rate in the last 16 years or so has been about doubling every 5 to 6 years. There was a time in the late 1980s when the rate of growth was more like 100% a year. But when you get to the 750 million machines or so that are visible, plus the others that are not, the doubling rate, understandably, has diminished. But still doubling every 5 to 6 years implies a substantial amount of demand for internet address space. Here are the actual statistics: 732 million estimated machines on the publicly visible network in January, and 1.8 billion users on the system. The other statistic, which is relevant in my view, is the number of mobiles that are in use, 4.5 billion of them, of which some fraction, I don't know how many, 15 to 20%, probably have internet access of one kind or another, and some are going to consume internet addresses as well, even if it's an ephemeral consumption. The implication of this is that internet address space is being consumed at a fairly high clip. And in fact, this is not a picture of today's Dow Jones Industrial Average. At least I hope it isn't. This is simply the diminishing number of IP version 4 addresses that are available to apply in the public internet. The choice of 32 bits was something that I chose in 1977 when I was still at the Defense Department, and this was a project that was only 3 or 4 years old, and with no clear indication that it was going to be successful. And so the question is, how much address space do you need to do an experiment? It seemed to me that 4.5 billion unique terminations was enough for an experiment. The problem, of course, is the experiment didn't end, and so